This is the last lecture on vectors. Therefore, I wish to take this opportunity to repeat what you have done earlier. We have seen vectors are quantities which have magnitude and direction. We have seen how a vector is drawn by a line segment with an arrowhead. We have seen how a vector is written, say vector A with an arrow on it. We also saw that if two vectors have the same magnitude and are in the same direction, they are equal. We also saw how we can add two vectors and get the resultant, how one vector can be subtracted from the other vector, how we can get the magnitude of the resultant and its direction using the parallelogram law of addition of vectors. Then we saw how vectors can be multiplied. We have dot product A dot B, which gives us the result A B cos theta, where A is the magnitude of A, B is the magnitude of B, and the product is A B cos theta. Then we saw the multiplication of two vectors, result of which was another vector. This is called vector product, and we write this as vector C is equal to vector A crossed vector B, and the magnitude of the product vector C is A B sin theta, where theta is the inner angle between the two vectors. We also learned that the product of two vectors can be another vector. This is called cross product. Cross product of vector A and vector B is vector C, given by, we write it as vector C is equal to vector A crossed vector B, and the magnitude of this vector C is A B sin theta, where A is the magnitude of A, B is the magnitude of B, and theta is the angle between them. And the direction is given by the right hand screw rule or the other rule, in which you curl your fingers and the direction of the thumb gives the direction of the result, the product vector. Now, the last thing that we have to do is the resolution of vectors. You are given a vector A in this diagram, and we want to find out its components along a set of axes, in this case axes x and y. How do you find that? You draw perpendiculars from the tip of the vector onto the x axis and onto the y axis. Then simple trigonometry tells us that the component A x is equal to A cos theta and component A y is equal to A sin theta. It is not necessary that they are as shown in the last diagram. They can be tilted as in this diagram, and we still can find components of vector A. It is the same vector A along the axes capital X and capital Y. Once again the same thing, the angle between them is phi, and therefore A x is A cos phi, and the component along the y axis is A y, which is equal to A sin phi. And from these two slides you must note that the components are not always equal. Components along one set of axes may not be equal to the components along another set of axes. Why do you find components? Let me remind you that when you derive the expression for the time period of a simple pendulum, then you have to resolve the vertical downwards vector g into components. One component goes this way, which cancels the tension in the string, and the other component gives us the force which moves the bob, and oscillations take place. Therefore, resolution is an important concept, and therefore we are trying to explain it to you. And when we take the components of a vector along a set of axes, this process is called resolution of the vector. Now, let us reverse the process. Suppose we are given A x and A y, then how do we find A, vector A? Again, simple geometry tells you that the magnitude of vector A is equal to the square root of a x squared plus a y square, whatever sector of x is you take. And the direction is given by, for the upper diagram, tan theta as the ratio between a y and a x, and for the lower diagram tan phi is equal to a y by a x. So, given components you can get the vector itself, its magnitude and direction. We introduce now the concept of unit vectors. As the name suggests, a unit vector has magnitude 1 and has a specified direction. It has no units and no dimensions. As an example, we can write vector A as A, which is the magnitude of A, times n cap, where n cap denotes a unit vector in the direction of vector A. Notice that a unit vector has been introduced to take care of the direction of the vector. The magnitude has been taken care of by A. As an example, we define a unit vector r cap as a unit vector along the line joining two masses m1 and m2. Then we can write the gravitational force between these two masses as the force F g equal to minus g times m1 into m2 by r squared into r cap. You remember, I hope, that I told you when we were doing the dimensional analysis that the two sides of an equation must always have the same dimensions. Now, you add another thing. If the equation is a vector equation, then the two sides must be vectors. As in this case, we have made the right hand side a vector by multiplying it by r cap. And since the force, say if I keep m1 fixed, m2 will be attracted towards m1. Therefore, the force is in the direction opposite to r cap, and therefore, this minus sign here in this formula. Electrostatic force between two charges can also be written in a similar fashion. Of particular importance are the unit vectors along coordinate axes. Unit vector along x axis is denoted by I cap, along y axis by j cap, and along z axis by k cap. Using this notation, vector A, whose components along x, y are respectively a x and a y, can be written as vector A equal to a x times I cap plus a y times j cap. This is how we write vectors now in terms of the unit vectors. Another vector B can similarly be written as vector B equal to Bx. Bx is the component along the x axis. So, Bx into I cap plus By into j cap, and the sum of these two vectors we write as vector A plus vector B is equal to Ax plus Bx whole multiplied by I cap. So, it is Ay plus By times j cap. By the rules of scalar product, you can show that the dot product of I cap with I cap is just equal to 1, because it is 1 into cosine theta, and the angle theta between them 0 degrees. Therefore, cosine of 0 is 1. I cap dot I cap is 1, j cap dot j cap is 1, k cap dot k cap is 1. On the other hand, if I take I cap dot j cap, then it is equal to 0, because the angle now between them is theta is 90 degrees and cosine of 90 degrees is 0. Therefore, I cap dot j cap is 0, j cap dot k cap is 0, and k cap dot I cap is equal to 0. And the dot product between two vectors A and B can be written as vector A dot vector B is equal to, again we write them into their components, Ax I cap plus Ay j cap into Bx I cap plus By j cap, and we can multiply using these, that I cap dot I cap is equal to 1, etc. We can get the result Ax plus Bx plus a y b y. Since this is a scalar, a dot b is a scalar, only we get the product. There is no vector on this side. It is a x b x, the component of a multiplied by the component of b along the x axis, then the component of a and the component of b along y axis. This is the dot product a dot b. Now, let us take an example. I am showing you here a graph in which there is a vector c, and the coordinates of vector c are 4 and 5, and therefore, we write this as 4 times I cap plus 5 times j cap. And what is the magnitude of c? Use Pythagoras theorem, easy. It is the square root of 4 square plus 5 square, which is the square root of 41. And the angle theta, which it makes with the x axis, tan theta is 5 by 4, or theta is tan inverse 5 by 4. Take another example, vector d in the same diagram, and this d is 6 I cap plus 3 j cap, and you can have the product c vector dot d vector and use the rules that I have stated earlier, and you will see that it is the square root of 39. Similarly, a dot p, you can take a dot b in this diagram. This is for your exercise, and you can see that a dot b is equal to 0. Why is it equal to 0 in this case? In this diagram, we see the vectors a and b are at right angles. When the vectors are at right angles, you remember that the angle between them is 90 degrees and cosine of theta is equal to 0, and therefore, in this case a dot b is equal to 0. The cross product of two vectors can also be written in terms of the unit vectors. For this, we first need the cross product of unit vectors themselves. For this, remember that the angle between unit vectors is right angle, that is, angle between I cap and j cap is right angle, angle between j cap and k cap is also right angle. And if we remember this, then I cap cross j cap you can easily get is equal to k cap. Why? Because the angle between them is 90 degrees, and the product has to be perpendicular to both I and j, and that is the z direction, and the unit vector in the z direction is k cap. Therefore, I cap cross j cap is equal to k cap, and you can use similar logic to get j cap cross I cap is equal to minus k cap, j cross k cap is equal to I cap, k cap cross I cap is equal to j cap, and I cap cross k cap is equal to minus j. Remember this, if I, j and k are in the same order, a I j k or j k I or k I j, as long as they are in this order, the sign is plus. If this order is broken, then the sign is minus. Look at this, j cross I is minus k, but j cross k is I, because j, k and I are in the same order. So, when the order is broken, a minus sign is there, and I cross I cap cross I cap is equal to 0, because the angle between them is 0, and sign of that angle is equal to 0. So, I cap cross I cap is 0, j cap cross j cap is equal to 0, k cap cross k cap is equal to 0. I cap cross j cap is equal to k cap, and like that. So, let us see how we can write the cross product now. The cross product C is equal to a x I cap plus a y j cap cross multiplied by b x I cap plus b y j cap, and now you use the rules which I have stated just now, and therefore, you can see that vector C would be equal to a x b y minus a y b x into k cap. Why k cap? Because we know that vector a and b are in the x y plane. Therefore, cross product has to be in the z direction. Therefore, vector C is a x b y minus a y b x times k cap, where a x is the x component of a, b y is the y component of b, a y is the y component of a, and b x is the x component of b. So, the cross product of two vectors A and B, where A and B are both in the xy plane, the cross product as it should comes out to be in the z direction. So, vector C is, you can see, in the direction of k cap. This result reinforces the fact that the cross product of two vectors in the xy plane is a vector along the z axis. Please remember this. If the vectors are in the xy plane, then their cross product has to be in the z direction, either this way or that way. Since this is going to be used by you very often, this is a very important concept. So, let me repeat this. The cross product of two vectors A, which is equal to Ax I cap plus Ay j cap, and B vector, which is equal to Bx times I cap plus By times j cap, their product is C, and if you use the rule of products between the unit vectors, you must get it along the k direction, because A and B are in the xy plane, therefore, their product has to be in the direction of z, and given the value of the components, you can find the magnitude of C. Let us take another example. Here we have got in this diagram vector E and F, and vector E is minus 5 times I cap minus 3 times j cap, and F is minus 3 times I cap plus 3 times j cap, and the vector G, the product vector, is perpendicular to both E and F, and E and F are in the xy plane. Therefore, vector G has to be perpendicular to this plane, that is in the z direction, and you can find that vector G is given by Ex Fy minus Ey Fx times k cap, and if you use the values of Ex, Ey, Fy, Fx, etc., then you can get this minus 24 times k cap. That means, now it is in the minus z direction, and you can work out by the rule that I have told you already, the right hand screw rule, that E cross F would be in the minus z direction. So, the point is that cross product is such a useful quantity. As I have told you earlier, there are many things like angular momentum, torque, Lorentz force, where we use vector product, and vector product is a very important concept, and many times we have to write the vector product in terms of the unit vectors, and therefore, please get familiar with unit vectors, work with them, do exercises from wherever you can get. I have given a few exercises here, and remember this concept. Let us take an example to understand once again the cross product between two vectors. Here we have taken vectors E and F. You can see in the diagram, and you can see that vector E is minus 5 times I cap minus 3 times j cap, and F vector is equal to minus 3 times I cap plus 3 times j cap. Now, if we use the rules of multiplication of unit vectors as we have done earlier, then you would get vector G equal to vector E cross vector F, E x f y minus E y f x times k cap, and if we use the magnitudes E x, E y, f x, f y, then you should be able to get that vector G is equal to minus 24 times cap k. That is, the vector G is along the minus z direction, and you can see from this figure that if you multiply E with F and use the right hand screw rule, you should get a vector which is perpendicular to this plane, but in the negative z direction. And I have repeated this many times because I feel that vector product is an important concept used very often in physics, as in angular momentum, as in torque, as in Lorentz force. We have to use it very often, and therefore, I have repeated it so many times for your benefit, so that in future you never have problem in understanding the cross product. Let me repeat the last time. The cross product of two vectors is perpendicular to both the vectors, and the direction of the vector is given by the right hand screw rule. If you remember this and if you can imagine a screw, then you can find out the direction of the product vector.